So charge of an alpha particle, we've got 3 types. Yep, so someone's already mentioned the 3 types of radiation you can have. You can have alpha, beta, and gamma. So let's write that down first in our notes. And for an alpha particle, yes, they are positively charged. Anyone know what they're made out of? We can fill that in as well. Made up of, so they're positively charged. That's because they're basically made up of helium nuclei. And a helium nuclei, or helium nucleus, is 2 protons and 2 neutrons. So that's what alpha is made out of. Yeah, next live, we're going to go through, I've already done a live on osmosis. I uploaded that today, I think. So check it out on YouTube. There's one on diffusion osmosis and active transport. So hopefully that'll help. All right, next question. Which type of radiation is the most penetrating? So penetrating basically means which one will travel through most materials. So penetrating means traveling through materials. So which one's the most penetrating? So most people, yep, we're getting it right. Gamma is correct. That's the one that passes through the most. It's the most penetrating. Which one's the least penetrating? So let's fill that in our table here. Gamma is the most penetrating. The least would be not radio. Radio is not a type of radiation. Radio is a type of electromagnetic wave. So don't get confused between this topic and electromagnetic waves. This is types of radiation. There's only 3, alpha, beta, gamma. Electromagnetic radiation, that's the stuff with radio waves, microwaves, infrared, all of that. So the one with the highest penetrating power would be, the lowest penetrating power would be alpha, and for beta, it would be medium penetrating power. Yep, moderately ionizing. Okay, next one. What type of decay increases the atomic number by 1? Atomic number. So let's remember, we got an element. At the top, we've got the mass number. At the bottom, we've got the atomic number, or the proton number. So what would a beta particle do? What can anyone tell me what numbers are on a beta particle? So let me know what you think and tap on the screen a few times. Yes, so beta is 0 and -1. So if you have beta decay, what does that mean? That means you have a nucleus. So here's a nucleus, and that nucleus is unstable and it wants to become stable. So this is an unstable nucleus. And to become stable, to become a stable nucleus, it needs to give off radiation. In this case, it's giving off beta. The answer for this is beta because it's giving off 0 -1. So what that's going to do, if you think about whatever this nucleus was, so this nucleus would have 2 numbers. I'll just call them A and Z. If it loses a beta, it's basically losing this -1, isn't it? If you take away -1, you're basically adding 1. So it causes the atomic number to increase by 1. So the answer is beta decay. Can anyone tell me what the other 2 numbers are? So what are the numbers for alpha and what are the numbers for gamma? Yeah, so that's what someone else is asking. What would it be for alpha, gamma? So let's draw beta while you guys tell me what you think that is. So beta is 0 -1. You might see it as 0 -1. I'll explain why later. Alpha is 4, 2. Good. 4 and 2 for alpha. And then for gamma, yep, well done. It's 0, 0. And for alpha, you might see it like this. You might see He42. Because remember, it is a helium nucleus. So you might see it as He42. So don't get confused if you see that. It could be both. Back to our questions. Here we've got an exam question now. So these are nuclear equations. So we figured out already that this alpha is being given off, yeah? And we know that this alpha is 4, 2. We want to work out what A is in the equation and what Z is in the equation. So it's basically a bit of maths. If you can think of the top part, so all the things at the top, you can think of it as one equation, and all the things at the bottom as another equation. Okay, so if we look at the top bit, we can say 210 is equal to a plus 4, according to what it says in the equation. So if we get 210 and move the 4 to the other side, a is equal to 210 minus 4, which gives you an answer of 206. Yep, well done guys, 206. And then we can do the same for the bottom one. Write another equation here. So 84 is equal to z plus 2. So we can minus 2 from 84, and that's going to give us 82. Yep, well done guys, 82 is the answer for that. So remember, for these nuclear equations, just separate the top part and the bottom part, and just think of them as two separate equations, just like here and here. All right, next one. We've got another one here with a beta this time. So remember, beta is 0 and minus 1. So let's do the same thing. Let's look at the top part here. 89 is equal to a plus 0. So it's basically 89 minus 0, which stays as 89. Well done, guys. And last one. So this is the question that we did before. Which one causes atomic number to increase by 1? So if you look at this one here, it's going to increase by 1 because 38 is equal to z plus minus 1. So if we move the minus 1 to the other side, we get 39. Well done, those of you who are getting these. So I hope that makes sense. If it makes sense, guys, just tap on the screen a few times. Just let me know if you want me to re-explain any of those. And we'll look at the mark scheme while you guys do that. So we've got A, 206. Yep, we got that. And for 82 for the second one, and then 89 and 39. That was fine. We got 4 marks. That all makes sense, hopefully. What is used to measure the activity of a radioactive substance? So something experimental that we use. Thank you for the gift. Yes, most of you are getting it. So just comment the answer, guys. It is a Geiger-Müller tube. Let's write this down on our notes. So Geiger-Müller tube, and what that does is it measures radioactivity or activity of a sample. For activity. What's the units that it measures in? Not ohms, nope, something else. Anyone else know? What's the units for activity? Becquerels, yes. BQ for short. Did I spell that right? Becquerels. Whoa, that's not even my handwriting. Okay, yeah, so becquerels is the unit for activity. This would be paper 1 if you're in AQA. All right, back to the next question. So Geiger-Müller tube and counter. What does gamma radiation consist of? What is it made up of? Okay, so we've already said that alpha is a helium nucleus. It's made up of 2 protons and 2 neutrons. And we might as well say what an electron, gave the answer away, what beta radiation is as well. So yeah, answer is electromagnetic waves. What's beta then? Let's add this in. Fast speed electron. Yep, good. Good. Table's looking good. We're nearly done with the table. Okay, another exam question now. So we've got a smoke detector this time. Question's asking, why is a source of beta radiation in a smoke detector more hazardous than a source of alpha? So why is beta more hazardous than alpha? This is not A-levels, no, it's GCSE, but this top question could be an A-level question. Beta travels far in air, whereas alpha doesn't. Sounds good. Because it's all to do with what, so in our table we wrote all the penetration powers, didn't we? So here in our penetration powers, we said that the most is gamma. So gamma is the most. Let me zoom out. And the least is alpha. Here this question's talking about alpha and beta. Beta has a higher penetrating power. So that's 1 mark we can mention there. What do you think the second mark can be? The second mark's all to do with the hazardous bit. So it's going to reach you. It's more likely to reach you because it's more penetrating. But why is that bad? What does radiation do? What's the name where? Yeah, it damages it damages cells because it can irradiate people. So it can irradiate people. So this is where we talk about irradiation and contamination. What's the difference between irradiation and contamination? Let's talk about that. It can radiate people and cause cancer. Yeah, cell mutation. What is irradiation? We're asking. So irradiation versus contamination. So these are just two ways that people can get exposed to radiation. Two different ways. Irradiation, yep, is when you're exposed to beams of radiation. Yeah, it's basically when you're exposed to radiation where the radioactive substance is not basically touching you. It could be like on the other side of the room, or it could be like a bit further away, but the radiation travels through the air and it can still reach you. Contamination is when it actually, the atoms itself, so the atoms of the radioactive source actually gets onto you. So you could either get it on your skin, or you could accidentally inhale it or eat it, like just single atoms of something that's radioactive. So contamination, we can say, is when radioactive atoms get onto an object. We'll say that object is contaminated. Irradiation is when radiation from a source travels through the air and affects a person, or it's usually a person that it affects. So out of the three types of radiation, I hope that makes sense, alpha, beta, gamma, which one do you think would be the most risk for irradiation? Which one will pose the highest risk for irradiation? Alpha, beta, or gamma? If it needs to travel through the air for irradiation to happen, which one is going to be the most dangerous? Yeah, it's going to be gamma. So gamma poses the greatest irradiation risk. So gamma is greatest risk. And then for contamination, which one will pose the greatest risk for contamination? That would be alpha. Reason is alpha is because imagine if you get alpha particles onto your body or into your body, you accidentally eat it, that's going to be more dangerous than gamma, because gamma can just pass through your whole body. Because it's the most penetrating, it can just pass through your body out of it. Alpha will stay in your body, and it's the most ionizing. So we'll talk about that in a second. It's the most ionizing, which basically means it's the most dangerous. So if it's on you or inside of you, alpha is the greatest risk. So yeah, those are the two marks. Okay, next we've got a nuclear equation again. We've got an alpha particle, so that's 4 and 2. So this time we want to find out these numbers, A and Z. So what do you think the two numbers are? So if we look at our two separate equations, we've got 223 plus 4 is equal to A. Yep. And the other one, we've got 87 plus 2, which is equal to Z. So you just add them together. People are getting the answer. Yep. Well done, guys. So the answers are going to be 227 and 89. Let's just check that on the mark scheme. So first question, beta radiation is more penetrating. We said that already. We can say it travels further as well. It can pass through the case. What it means by that is the case of the actual smoke detector, because it has like a plastic case. It can pass through that. And then beta could irradiate people who are near the smoke detector, or you can say it passes through the skin. So that was fine. We got 2 marks there. And for the two numbers, we also got 2 marks. Okay, next question. Which is a feature of beta particles? Let me know in the comments and tap on the screen a few times. So they're positively charged. They can be absorbed by a sheet of paper. They have virtually no mass and charge of -1. They increase the mass number of an atom. We've got 2 answers so far. We've got C and B. Let me put a star here. Star here. Any other answers? Let me know. So far we've got C and B. So most people are saying C. They virtually have no mass and a charge of -1. So they're definitely not positively charged. The only one that's positively charged is alpha. They increase the mass number of an atom. No, they increase the proton number because there's 0 minus 1. They can be absorbed by a sheet of paper. No, they cannot. They get absorbed by aluminium. We'll add this in our notes now. The answer is they have virtually no mass and a charge of -1. And the reason for that is because, remember, they're made up of electrons. High-speed electrons. So the electrons have a charge of -1 and they pretty much have no mass. So let's write down what each one stopped by. So alpha, we said paper. Beta, aluminium. What about gamma? What's gamma stopped by? Gamma's not stopped by skin. No, it's not. So which other one stopped by skin? Yep, gamma's lead. You can say lead or something else. So gamma stopped by lead. Something else. One of these is stopped by skin. Which one stopped by skin? Because that's quite important. And then we've got aluminium here. We can say concrete. Yes, concrete you can use to stop the gamma radiation. And then for skin, it's alpha. Alpha can't pass through skin. So it basically can't get inside of your body. And when it's inside your body, it can't leave your body because the skin blocks it. So stopped by paper, skin, and also few centimeters of air. So we can actually also write air. It doesn't travel far in air. That's why it's so hard to get irradiated by alpha particles. And then we might as well finish this off with the ionizing power. The most ionizing, I said, was alpha. Least is gamma. And beta is medium. So we're done with the table now. So the feature of the beta particles, they virtually have no mass and a charge of -1. Okay, in the context of irradiation and contamination, what is the main concern when we're working with alpha particles? This is what we talked about. Difficulty in detection, penetration through skin, ability to cause burns, inhalation or ingestion of alpha particles causing internal damage. So what is the greatest risk when it comes to alpha particles? The answer is going to be D, yes. Because if you inhale or accidentally eat alpha particles, they're going to be the most ionizing. So they're going to cause the most damage to your cells. Next question. We've got another exam question here. So a teacher wants to find out what nuclear radiation is emitted from a source. So is it alpha? Is it beta? Or is it gamma? The teacher placed different barriers between the source and a detector. So imagine here we've got the source here. That's the source. And we've got a detector here. And in between we're putting something in. So this is the barrier. And the teacher records the count for 30 seconds. So basically this is a Geiger-Müller tube, yeah? So it's being used to measure how much radiation is coming out of this source here. The source is going to emit radiation and it's going to go to the Geiger-Müller tube and it's going to give a reading. The higher the reading, the more particles that have gone through. So the question is asking which nuclear radiation, so is it alpha, beta, or gamma that was emitted by the source? And it's 4 marks, guys. So really think about this. Some of you are saying something that's 1 mark. So people are saying alpha. Why is it alpha, do you think? So we got to look at the numbers here. So there's a high reading when there's no barrier. So that first one is no barrier, right? So whatever it is goes through the space in the middle and reaches the detector. So that's the radiation you have at the start. Then if your barrier is paper, then your radiation, your reading has gone down quite a lot, which tells you there must be alpha, but that's only 1 mark. So alpha radiation, because what's the second mark for? Let me see what you guys are saying in the comments. Because it's stopped by paper. Yep, good. So that's 2 marks. What do you think the other 2 marks are for? The other one is this part here. Look at this. Once you add aluminium, it goes from 149 to 0. So that means the aluminium has also stopped something. The paper has stopped the alpha, but remember what aluminium stops. If we look back at our notes, we've got here, beta is stopped by aluminium. So there must also be beta radiation as well. And you can have that. You can have something that gives off two types of radiation. Because it goes down after you put the aluminium, it means that there's beta radiation as well. And the reason for that is because it's stopped by aluminium. So it'll be 1 mark here, 1 mark here, 1 mark here, 1 mark here. Did that make sense, guys? Tap on the screen if it made sense. Would you get an extra mark for saying beta? Yes, that's how you get all 4 marks. So if you just say alpha and stopped by paper, then you'd only get 2 marks. You have to also identify here that there is beta as well. Not gamma, because once you add lead, there's no difference. It stays at 0. It's 0 and then it stays at 0. It's not making any difference. So it doesn't give off lead. It goes to aluminium is enough to make it go to 0. If there was gamma present, this wouldn't be 0. This would be something like 50 or something. This would have a number in it. So no, you do not talk about lead. You don't need to talk about lead. You don't get any marks. I'll show you the mark scheme. You don't need to talk about lead. So radiation is stopped by paper. Some of it is stopped by paper. That's in brackets, so you don't need to say some. So it does emit alpha. So that's 2 marks there. Some radiation passes through paper, but is stopped by aluminium. So that's this part here. It's stopped by aluminium. So the source emits beta, but it does not emit gamma. So those are the 4 marks. Okay. Does that make sense, guys? Yeah? Okay. How often do I do these lives? Usually Fridays, Saturdays, twice a week. Tomorrow's one, I might move to Sunday, but I'll let you guys know. I'll put a story up or something. Okay, next up. Which type of radiation is least penetrating and can be blocked by human skin? This is a quick one, guys. Tap on the answer. Not tap on the answer. Comment the answer and tap on the screen a few times. Yeah, I post on my story, like on the day I post what topic I'll go through. And the next one is going to be biology, and I'll be going through bioenergetics. So that's a really important topic that can come up in any paper. That's photosynthesis and respiration. That's what the next one will be. Yep, good. Well done, guys. Alpha. If an element undergoes alpha decay, what happens to its atomic number? What do you guys think? Comment the answer and tap on the screen. Atomic number. So is that the top or the bottom? Mass number at the top. Atomic number at the bottom. And remember, alpha is 4,2. So the atomic number, if it loses alpha, then it's going to change by 2. But the question is it going to be increasing or decreasing? Most people are saying increases by 2. So everyone's saying this. Any other answers? Someone said C. Think about it, guys. It is either B or C because it's 4,2. Remember, you're starting off with a nucleus. It's giving off alpha. So the alpha particle is being taken away. So the 4 and 2 is being taken away from this. And then it becomes stable. So whatever this is, it's losing alpha. So you have to minus 4 and 2. So that means it's decreasing by 2, not increasing. It's a common mistake. Hope that makes sense. You're losing the alpha. So you're losing the 4 and you're losing the 2. Therefore, the top number decreases by 4. The bottom number decreases by 2. Next one. What does the half-life... Okay, so this is another important part of radioactivity. What does the half-life of a radioisotope indicate? Let me know what you think the answer is and tap on the screen a few times. A, B or C. The time takes for all the nuclei to decay, the time it takes for half of the nuclei to decay, the time it takes for the radiation to reach half its initial intensity, the time it takes for radioactivity to double. It's definitely going to be one of the ones with the half in it, isn't it? A or C. Not for all of it to decay, not for it to double. And it's this word intensity that makes this incorrect. The definition of half-life, we can write down in our notes. The time taken for the number of undecayed nuclei to half. So remember, guys, I'll be uploading this whole live on YouTube and with these notes attached in the comments as well. Time taken for the number of undecayed nuclei to half. So you can either say that, or you can say time taken for the activity to half. So the number of becquerels to half as well. Time taken for half of the nuclei to decay. That's basically the definition. The number of undecayed nuclei to half. Okay, exam question now. Radioactive dust from nuclear weapons testing settled in the desert. This is called radioactive. What do you guys think? Vote your answer. Contamination, irradiation, ionization, or decay. Radioactive dust from nuclear weapons testing settled on the desert. It's settled on the desert. Okay. Getting a mix of answers here. So what do we have so far? We've got decay, irradiation. We've got contamination. So no one said ionization, so that's good. So keep voting, guys. What do you guys think it is? So it's settled on the desert. So something that's radioactive. So this dust is radioactive, has settled on the desert. So look at what contamination says. When radioactive atoms get onto an object, it has settled on the desert. So the radioactive atoms, which is the dust, has settled on an object. The answer is contamination. Not irradiation, because remember what irradiation is. That is when you have something that's radioactive here and someone is getting hit by the radiation from far away. Contamination is when the actual particles get onto the person. Here, the actual particles are getting onto the desert. So the answer is contamination. Hope that made sense. Next, the graph below shows how activity of tritium in the sample taken from the desert changed with time. Determine the activity of the tritium sample in 2007. What do you guys think we need to do here? Let me know. We're going to have to use this graph in some way. How are we going to find out the activity in 2007? So you can do 2007 minus 1992. That's going to tell you how many years it took, because here we don't have years, we have the time. So if we work out how many years that is, it's 15, isn't it? When you do 2007 minus 1992. So we need to find out what the activity is after 15 years. So go to 15 here. You would get a ruler in your actual exams, and you want to find out the activity. So go here, and it's about halfway. If you draw this line correctly, it's about halfway there. So the answer is, yep, well done, 35 becquerels. Does that make sense, guys? No, it's not asking for half-life here, so you don't need to do, I know what some of you guys said. Some of you thought that you get 80, you go to 40 because you do half of it and then work out what half-life is. That is not what you do. So just checking that on the mark scheme. Contamination, yes, we said that. So we got 1 mark for doing 2007 minus 1992 and then drawing it on the graph and reading it off. You get an answer of 35. Carrying on with the question, how much time did it take for the activity of the tritium sample to decrease from 80 to 40? What would we do here? So this is another 1 mark here. So again, we're going to have to use the graph somehow. From 80 to 40 becquerels. So it's starting off at 80. We would go, yes, so we would go to half, which is 40. And this time we're going to do it the other way around. We're going to draw a line across and we want to find out the number of years. It's exactly halfway between 10 and 15 years. So that would be 12.5 years. Well done, guys. You guys are getting it. What is the half-life of tritium? This is a 1 mark question. They haven't even given you space to do any working out. So that's a clue here. What do you guys think the answer for that one is? Let me know. Not 10. So the clue is there's no working out needed because they haven't given you any lines. It's a 1 mark question. So it's something you need to state. Not 7.5 either. Half-life. Remember what half-life is. It is the time taken for the number of undecayed nuclei, or the activity to half. We're looking at activity. So it's the time taken for the activity to half. The activity, what we looked at in the previous question, was the time taken for the activity to half. It went from 80 to 40. So the previous question, we actually did work out what the half-life was. So the answer is what we got in the previous question. That's why there's no lines there. There's no working out to do there. It's 12.5. Next up, the sample started with 45 billion atoms. After 4 years, it had 36 billion atoms. Calculate the percentage of tritium, the sample, that remained after 4 years. It's a quick calculation. It's not, there's no equations here. This is just a bit of maths here. What would we do here? Yeah, this is physics, guys. So we've got the sample at the start. We've got how many atoms we have at the start. We have how many we have after four years. And we want to work out the percentage that remained after 4 years. Yeah, straightforward. 36 billion over 45 billion. And then times it by 100. You don't need to do billion. You can just cancel those out, isn't it? You can just do 36 over 45. And then times that by 100. And that gives you an answer of yes. Well done. 80%. 12.5. Here it says allow the same value as your answer to C. So if you got part C wrong, if you read it off wrong, but then you realized that part C was the half-life, you would still get the mark, even though the answer would technically be wrong. So this is what we call error carried forward. This does happen sometimes in calculations where one calculation leads on to another calculation, even if you got the previous one wrong, but you do the method in the next one right, you can get error carried forward. And then here, yep, look, here they did 36 billion over 45 billion, but you can just do 36 over 45 times by 100 to get the answer. What type of radioactive decay results in the emission of a helium nucleus? Quick answer here, guys. Let me know, vote your answer and tap on the screen a few times. Helium nucleus. So remember, we had one which is a helium nucleus, we had one which was an electron, and we had one which was an electromagnetic wave. So it's one of these. It's going to be C, alpha. Yes, well done. Which is the most dangerous type of radiation to human health when outside the body? What do you guys think? Outside the body. Definitely not neutrons, either alpha, beta, or gamma. Outside. What's the answer? Vote and let me know. C. Yes. Well done, guys. Answer is C. What is the main advantage of using gamma rays in medical treatment? What do you guys think? This is you got to kind of apply your knowledge here to figure this out. Comment what you think the answer is. Penetrate deep in the body. So we're getting B. Most people saying B here. Do we have any other answers? Most people saying B, 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 B. Someone said D. They're easily detected by standard medical equipment. No, they're all detected. Alpha, beta, and gamma will all be detected. So that's not the case. They have short half-life. You can't say that. You don't know. The fact that it's gamma doesn't mean it's long or short half-life. The type of radiation doesn't tell you anything about the half-life. That all depends on the source itself. They're easily absorbed by skin, or they can penetrate deep in the body tissue. If you want medical treatment, you're using it to kill tumor cells usually. That's what gamma radiation is used for. So you actually want it to go through the body to attack the tumor cells. So the answer is B. Okay, I'll give you guys a few seconds to look at this one. You got to think about this one. Which isotopes? We've got 4 isotopes here, A, B, C, and D. Write the isotopes A, B, C, and D in order of increasing stability of the nuclei. What do you guys think this is? This one's not very straightforward. Increasing stability of their nuclei. This is all to do with how quickly they decay. Because if they're more unstable, they're going to decay faster. They're going to give off a lot of radiation. So how quickly they decay. How can you work out which one is giving off the most radiation from that graph then? You had a test. You had this question before in your year 10. Kept getting it wrong. Okay, hopefully this time it'll make sense. It's yeah, so this is a question from I think 2 years ago. So someone said A, B, D, and C. It's nothing to do with the units, no, but it's the activity. So you can see all of them are going down. Anything that's radioactive is always going to go down. The more unstable they are, the faster they're going to go. So we want it in terms of increasing stability. So that means we want the least stable on the left, the most stable. So the least stable one needs to be the one that gives off the most radiation and drops in activity the fastest. What's a fair way of comparing how fast they're decaying? That would be to look at their half-lives. So let's look at their half-lives. Let's start off with D, okay? So D starts off at 150. Its half-life is going to be when it's half of 150, so when it goes to 75. So let's see where it reaches 75. So it's around here. So this is D. It has a half-life of around 7, we'll say. The next one, we'll look at C is pretty tricky to look at. We'll look at B next. So that's 250. It starts off at 250. We want to go to half of 250. So that's around 125. Find the gradient. No, I wouldn't try and find the gradient here. It's going to be tricky to find a gradient. Could help actually. The less steep it is, the faster it's decaying. But it's more to do with this half-life. So let's look at the half-life here. The half-life here is around here. So that's for B. Now we've got to look at A and D. So we're going to come across a problem in a second. So not with A. A is fine. We've got 400. Half of 400 is 200. So let's draw a line at 200. And you can see here, the half-life's even longer. So it's taking even longer for it to half. So the problem we're going to come across is for C. It starts off at 100. We want to work out how long it takes to go to 50. But it never reaches 50. It's getting lower and lower. So what does that tell us? That means, when is it going to reach 50? It's going to reach 50 way over, like, off the page, isn't it? It's going to be much, much longer. So we just know that the half-life of C is going to be much greater. That's going to be the greatest. So the final answer is D, B, A, and C. And it's all to do with half-life. Does that make sense, guys? Tap on the screen if it makes sense. So we've shown the half-life, and we can say D has the shortest half-life, so it's less stable. Saying something like that is good, and then you can say the opposite for C. I'm just going to write opposite for C here. But the marker would see, if you've done all of these calculations, they'll see what you're doing here, and they should give you the 3 marks. D has the shortest half-life, so yeah, so I think that should give you all 3 marks. Let's see what we're saying. Yes, you guys are getting it. Can't you guess by looking at them? Yeah, you can, kind of. But you need to, the way you guess is you have to guess what the half-life is. And yeah, you can kind of look at how steep they are at the start. Look at the gradient at the start. This tricky thing with gradient is because the gradient is constantly changing. They're all curved. It's hard to see. But to get the mark, you have to mention half-life. So to get all 3 marks, you have to talk about half-life here. Am I doing a chem live anytime soon? So I've got, I did one on Wednesday, which I put on YouTube. That was on bonding, and the next one will be next week. I'll do another one next week. I'm not sure what it'll be on. And yeah, I only do this for science. Sorry. Can't help you with anything else really. Maybe maths, but I don't do. I don't do maths. D, B, A, and C. Yes, we got this mark. A substance with longer half-life has more stable nucleus. We mentioned that. So answers are increasing half-life. Yeah, we mentioned that D has the shortest half-life. And what was it? C, I think. C had the longest half-life. So that was fine. Okay. Nearly done, guys. Which safety measure is important when handling radioactive substances? We got one more exam question, I think. I think it's a 6 marker, which we can go through together. Which safety measure is important when handling a radioactive substance? A, B, or C? So we're saying C mostly. Yep, lead-lined gloves. Because remember, gamma doesn't pass through lead. Neither does alpha or beta. Nothing passes through lead. So using lead will guarantee that your radiation won't come out and harm you. So that's the best thing to do. During alpha decay, mass number of the nucleus decreases by. Okay, let's have a vote here, guys. Let me know what you think the answer is and tap on the screen a few times. Think about this. There's two possible answers here that people will get confused with and probably make a mistake. So the mass number of the nucleus decreases by, what do we think? B and D? See it? Yep, this is what I thought. People are going to think it's either B or D. It is one of these two, guys. It's not this, it's not this. Which one is it? B or D? Don't fall into a trap. It said mass number. So remember, we've got alpha, the top number is 4, the bottom number is 2. So I understand why everyone said 4 and 2. Mass number is the top one. Remember that. Atomic number is the bottom one. So the answer is going to be D. It's going to be 4. Which particles are emitted from the nucleus during beta decay? Quick one, guys. Very quick one. Beta. Yep. Answer C. Remember, in our notes, beta are high-speed electrons. That's what they're made up of. Okay, last exam question, guys, before we have a few more multiple choice questions, and then it'll be the end. This, we're going to recall everything that we learned from that graph. Give me quick points, guys, that I can add. Explain the differences between alpha, beta, and gamma. It's basically recalling that whole graph. This came up a few years ago. So you're going to divide your answer into 3 and just list out what you can say and try and get 6 marks. What do we say? Why don't you guys type it in the comments? How do electrons come from the nucleus? It's radiation. That's what happens in nuclear radiation. You get it's complicated. You don't need to know why, because that's A-level physics. You just need to know that it can happen when you have an unstable nucleus. An electron can get given off. That's a beta. Sometimes a helium nucleus can get given off, and sometimes electromagnetic radiation can get given off. Alpha is the most ionizing. Yes, we can say that. Most ionizing. We can say, therefore, gamma is least ionizing. That's going to get us a few marks. And beta is moderately ionizing. What else can we say? Alpha is least penetrating. Yes. So remember, that's the opposite. That's the easiest way to remember these two. They're the opposite order, penetrating and ionizing. So alpha is least penetrating. Gamma is most penetrating. What else? What can it pass through? Yes, we can say alpha is helium nucleus. So we can say what they're all made up of. Well done. So this was a helium nucleus. The other one was, so beta was a fast moving electron, and gamma was EM radiation, electromagnetic radiation. You could talk about the charges. Yep. So this is positive, beta is negative, and this one has no charge. Waves can't have any charge. Electromagnetic waves do not have any charge. Let's add that here. What else can we say? What they get stopped by. So here we can say stopped by skin. So if you memorize that table, you've basically got all your marks. This one's stopped by aluminium. Yeah, exactly. So you can talk about paper as well. That's fine, yeah. And stopped by, remember this one was lead/concrete. You can't talk about wavelengths because they don't have different wavelengths. Only gamma is a wave. The other two are particles. I think you're getting confused between radioactivity and waves, electromagnetic waves. You're thinking about the electromagnetic spectrum. If that was the question, you can talk about wavelengths, but not this one, because these aren't waves. Only one of them are waves, so you can't talk about wavelength. Next live will be either tomorrow or Sunday, probably. It'll be in a few days. I'll put it up on my story to let you guys know, and I'll upload the live that I did on Wednesday, the one on bonding. I'll do that. I'll try and do that tomorrow. So let's see what the mark scheme says for this one. What have we talked about? Helium nucleus, yes. Least penetrating, yes. Stopped by this. Shortest range, we didn't. Yeah, we did talk about that actually. No, we didn't talk about that, but that's fine. You don't need to mention everything. Few centimeters of air, we didn't mention that. Most ionizing, yes. Has a charge of +2, that's fine. Talking about that. Penetrates, yes. We said moderately penetrating, stopped by aluminium. Didn't talk about range. Ionizing we talked about. Yes, so we're basically talking about the first few and the last two. That's more than enough for 6 marks. What paper is this? I think this was either 2022 or 2021. It was very recent. It wasn't last year's paper though. That's what's going to come up in your marks probably. What remains constant in different isotopes of the same element? So I think we got 2 more questions after this. And then we'll call it a day. What remains constant? The number of protons. Yes. Number of protons. If you ever change the number of protons of an element, nothing happens to it. But if you change the number of neutrons, it becomes an isotope. So definition of an isotope is different neutrons, but same number of protons. The mass number of an atom is the sum of its protons. And so this is a bit of chemistry as well, guys. Does D not? Let's see what the answer. Electron configuration. No, it's not. It's not D. Sorry, I had to go back. Someone asked. Is D the answer? No. Electron configuration wouldn't be the same for an isotope. Oh, wait. Let me think about that. No, you're right. Electron configuration would be the same. The number of electrons would be the same. It's just the nucleus that wouldn't change. Yes, you're right. For this one, the answer would be C or D. Because if you have an isotope, it will still have the same number of electrons. So the electron configuration would be the same. Well pointed out there. But they wouldn't ask you about electrons, really. Electron configuration in physics. So hopefully they won't ask you something like this. They'll ask you about the protons. They won't mention electron configuration. And yes, for this one, everyone's saying neutrons. Yep, protons and neutrons. That's what mass number is. And final one, guys. Vote what the answer is. And I'll tell you guys, post this on YouTube in a few days' time. With all the questions that I put up here. I think I'm going to put a few more questions as well. And all the answers to them. As well as the notes, all the notes that we've written. So subscribe to that if you want to get updated on any new lives that I've done, or look at any of my past lives or any of my videos, the longer videos. You can go into that. It's the same name as Flash Revision Lab on YouTube. And yes, answer, ionization is a process that creates, okay, so this technically in chemistry could be any ion. It doesn't have to be positive ions. Ionization can be positive or negative ions in chemistry because it can lose or gain electrons, right? If it loses electrons, it becomes positive. If it gains electrons, it becomes negative. But in this topic in physics, ionization is basically when a type of radiation knocks off electrons from an atom. It always forms a positive ion. So whenever you ionize an atom due to radiation, it's positive ions that are formed. It's not negative ions. So that's why I wrote positive ions here. I should have written ions because technically in chemistry it would be any ion formed. But yeah, in physics, it's pretty much always positive ions. All right. Thank you, guys. We'll call it a day and I'll update you on my next live. So like I said, it'll either be tomorrow, usual time, which is 5. If not, it'll be Sunday evening. No problem. Thanks. I'm happy that I'm helping people out here for your mocks. It's good to hear. And yeah, good to hear it's helpful as well. Like I said, I'll keep posting a few videos as well, so just comment on them. If there's any specific topics you guys want to do, then comment on my videos and let me know, and I'll try and do like all the big topics for mocks / for summer as well. All right, have a good evening, guys. I'll see you in a few days' time. Bye.